Thank you very much, everyone, for taking the time to join us and have the opportunity for us to present on one of our more recent developments in the germanium detector line, the Sagewell detector. We'll be going over in this presentation today some of the unique technology features of this detector and what the advantages are, and put it in a position to show what makes this detector really unique. It's part of a broader product line, so we'll also give you an overview of the different types of Sagewell detectors that we offer, and to give comparative analysis so that it allows one to be able to select the proper detector for their particular application. In addition, the unique features of the Sagewell detector allow access to many other features that we offer as part of our overall Canberra product line, and we'll cover some of those new features, how the Sagewell fits within these new features as well. And then finally, for this presentation, I'll turn the presentation over to my colleague Doug Van Cleef, who will cover some specific application examples and benefits. Now, one of the key advantages that the Sagewell detector brings to a laboratory count room is improving on the sensitivity. And to help give example or a context for which we can describe these improved activities, I want to remind everyone of the concept of the minimum detectable activity. This is a concept in which addresses the question of if you make a measurement and you don't see any activity in that sample, that you can address the question of what is the maximum of activity that could be in that sample. There are many different ways to address this concept, but they all have similar fundamental approaches in terms of producing that sensitivity. And to discuss that, I would like to just introduce the Curry formula for calculating the minimum detectable activity, or the other concept is minimum detectable concentration, which is related to minimum detectable activity by the concentration of the unit mass, whereas activity represents the whole sample, the activity in the whole sample. Again, there are many different ways to approach this calculation, but they have fundamentally similar approaches in terms of how you reduce or minimize this minimum detectable activity of your system. One of the most important ways to reduce your system is to maximize the efficiency of your sample. And you see from this formulation that improving the efficiency of your sample will reduce your minimum detectable concentration in a linear manner. If you decrease the background in your system, that will also reduce your minimum detectable concentration, but in approximately as a square root. By adjusting the time, that's another way that we can reduce the minimum detectable concentration. And by changing the mass of the sample, increasing the mass of the sample, this also increases the sensitivity. So I want to keep these concepts in mind, that improving efficiency gives you the best level of performance, and reducing background gives another level of performance in reducing the minimum detectable concentration. So let's start by considering the example of having a small sample of material. In this case, let's assume a 1 milliliter sample of water. And if you have a traditional closed-end type of detector, germanium detectors such as a SEGI detector, REGI detector, or a BEGI detector, the best way to maximize the efficiency for this type of system is by taking that sample and spreading it out in a very thin way, much like a filter paper. And if one does that, one can obtain efficiency responses as I show here on the chart to the right. So this chart is a plot of the absolute efficiency response, where 100% means that all gamma rays emitted from the sample are detected, versus energy. So, and this is detected as the full energy efficiency, as detecting the peak. And if we look at these, one will see that there's a maximum that the Beji response gives the best efficiency response for these closed-end detectors. However, even that detector is limited to the maximum solid angle that you can cover, and it's about 25% of the overall solid angle, and that represents about the maximum efficiency that you could get for this type of sample with a closed-end detector. Now, the better approach to do this is to take that sample, and if you could surround the detector and increase the solid angle, you can further improve the efficiency. And I show that in this example where the sample is now placed inside the detector, surrounding with a well surrounding the sample. And if one does that, one increases the solid angle coverage up to nearly 100%. 80% is about the practical maximum because you still have a hole on the end. But if we look here at that efficiency, the gains in efficiency are tremendous. So when measuring small volume samples, placing a sample inside a well is a superior way to be able to really maximize your sensitivity, and therefore represents minimizing the minimum detectable activity. So this is not a new concept. Well detectors have been around for many years, and in fact, the traditional well detectors have been part of many different count rooms with many different environmental science applications. However, historically, because of the design and the technology based on the traditional well detectors, they suffer by requiring a larger internal contact, which increases the capacitance of the detector. What that means in practical terms is the energy resolution decreases proportionally to the size of the hole that's used in the well detector. And so this is illustrated in this figure here on this plot, where this is the full width half max energy resolution versus energy for different types of detectors. Our Beji detector, which is a low capacitance type detector, has the best energy resolution for a given given model type, and that's represented here with this line. The middle line is for coaxial detectors, which are SEGI type detectors, our Regi type detectors, and extras. Now, you can see in this that the traditional well detector has a much reduced energy resolution even to our coax detectors. While we indicated that there is a resolution degradation, the increased efficiency really makes these detectors desirable for certain specific applications, despite the fact that with the reduced energy resolution, this would reduce your background effect, or this would increase your background, which reduces your sensitivity. But since that goes as the square root, you can still get a gain in your overall minimum detectable sensitivity. However, because of this, you tend to be limited because of the poor resolution. One tries to keep the well sizes to a minimum, so you're limited to very small sample sizes. There historically has not been an easy way to do automated cascade summing, coincident summing corrections. And because of the limitations of the energy resolution, it's not really suitable for measuring other larger type samples, because this there's typically the other detectors have a much better performance in that area. And another element related to this is they also tend to be more sensitive to microphonics than other types of detectors, and that limits its use in electrical coolers. So a few years ago, we introduced the SAGE well detector, which stands for small anode germanium detector. And really what it is it's a revolution in the design of well type detectors. It's fundamentally starts from the concept of the Beji type point-like contact of the Beji detector, which is inherently a low capacitance detector. And because of low capacitance, that also means it's has a superior energy resolution. And we can see in this particular graph here, this is again that same chart of the full width half max versus the energy response, the same curve from the previous plot. And the expected energy resolution of Sagewell detectors is much, much more comparable to the Beji detectors. And therefore, one can have large detectors for samples in the well that have a response that gives you Beji-like energy resolution. So now, with these types of detectors, one no longer has to sacrifice energy resolution in order to be able to maximize the solid angle coverage by putting a sample in the well. Another advantage that the Sagewell detector brings is it's no longer sensitive, the size of the well is no longer giving sensitivity and reduction in energy resolution to the detector. So one can use much larger size sample wells without having to sacrifice energy resolution. The design also brings up other features that we'll discuss later in the talk that bring in advantages such as compatibility with our LabSOCS efficiency calibration software and our automated Cascade Summing routines. So before we get into those extra details, I'd first like to go over the range of detectors that we offer within this product line. The Sagewell detectors are indicated in this table here. The model number indicates GSW, which indicates the Sagewell geometry, and the number after represents the approximate volume of that particular detector. So we offer ranges from GSW 120 up to GSW 425. To give you a context of how big that detector is in the context of our standard coaxial detectors, a GSW 120 detector has approximately the same volume as a GC 30 detector, so a detector with 30% relative efficiency. The GSW 425 would be equivalent to a coaxial detector of greater than 100% relative efficiency. One will see that from the models of the detector that because we no longer have the sensitivity in the size of the well of the detector, we offer as standard the larger 16 millimeter well size that we had in the traditional well detectors. And the well depth is the same 40 millimeters that we've had previously. The resolution specification for these detectors is comparable to coaxial detectors, a little bit less, but within that same range. But the low energy full width half max resolution specifications are equivalent to our Beji detectors. So they're very good resolution detectors. It's interesting it should be worthy noting that because of the design of these detectors, the end caps are a little bit larger than our typical detectors in that size. So this should be noted in the cases where one is making measurements with Marinelli beakers to note the size of the end cap to make sure that one has the right size beaker. A fifth detector, which I didn't talk about within this product family, is the GSW 275L. It's a mid-size detector in this range, but what makes this detector unique is that it has a 28 millimeter diameter well, so it can accommodate samples of diameters up to an inch or slightly more than that. Again, because of the features of the Sagewell detector geometry, there is not a resolution degradation to be able to accommodate this larger well. Excuse me. So the Sagewell models themselves, I illustrate here the differences between them in terms of efficiency performance by looking at the efficiency for a 1 milliliter water sample in the well. This is, again, the absolute efficiency versus energy. And one can see that, that at low energies or mid-range energies, the detectors have a very similar efficiency response, and then a correspondingly wider distribution proportional to the volume of the detector as you go to higher energy gamma rays. It's also noted here as in a dotted line the GSW-275L efficiency response, and we'll talk about that in the following slide. So in this slide, as I mentioned, I'd like to highlight the advantages of the 28 millimeter well for the GSW-275 detector. In this plot, I change the vertical axis slightly by not talking about just the absolute efficiency, but talking about the efficiency times the mass of the sample, which is a concept called the Massa Metric efficiency. So if you recall from the MDC formula, if we can increase both the efficiency and the mass, these both have linear effects in reducing the minimum detectable activity. These are plots versus energy, and the first trend I'd like to note is the GSW-200 that was from the previous figure. This detector, if you recall, has a 16 millimeter well. It's the red dashed lines here. And this is the efficiency response for a water sample with the dimensions of 14 millimeter diameter and 40 millimeter high. So that represents a vial that fills the full diameter of the well and the full height of the well. If we take that sample and remove it and put it directly into a GSW-275L without changing the geometry, one gets the light blue curve that essentially mirrors just below the GSW-200 curve. And so one sees that the efficiency doesn't change dramatically there, but that's because the well is a wider opening, and so it's a little bit less solid angle coverage. However, if we take that same volume of material and put it into a vial that's suitable diameter for the 28 millimeter, one can get a geometry that is 26 millimeter by 11 millimeter high. This is the same volume of material as the 14 by 40. And just by changing the geometry to be suitable for the larger well, one already observes a higher efficiency response. Now, if we take that same vial and fill it to the top of the well, one can see then the advantage of the increased mass that you can put into the well detector to improve the Massa Metric efficiency even more dramatically. So this illustrates the advantage of the larger well. And again, there's no sacrifice in energy resolution to make this choice. Now, while this is still a relatively new detector technology, we are continuing to work to further improve and enhance the sensitivity of this device. And I want to share a couple of those new developments that we're going to be implementing either now or very, very soon. And the first I'd like to highlight is the advance of the technology in creating the inner contact within the well. So in the early technology of the sage well, we had a thin contact within there that gave a good efficiency response, good low energy efficiency response. However, it was a little bit thicker than what we're typically wanting to achieve, and it also was not stable with temperature. So if a detector was stored warm for a long time, this layer would migrate and get thicker. So that led to us recommending that detectors be kept cold, not to be kept warm for extended periods of time. Now we have a new technology that's a stable N+ contact, similar to the contact that we have on veggie detectors. The advantages of this is it's much thinner than our current contacts, and it's stable with temperature, much like our veggie detectors. And I showed the example of the benefits of this thinner contact, where, again, I'm showing the absolute efficiency on the vertical axis versus energy. The gray curve is the original efficiency response of our standard well detector contact, and the blue curve is the efficiency response for our new contact technology. This contact technology is a process that will be applying to all new SAGE well detectors. There's no special ordering for this, and it will be available going forward. The other new development that we've done is we've developed a well insert that is less attenuating than our aluminum end cap material, and also is of ultra-low background characteristics. So for our ULB offerings on the SAGE well detector, we will have as standard a new ceramic well insert. Again, it's less attenuating than our current aluminum end cap, but still has the same ultra-low background properties. To see the additional benefit, we highlight on this efficiency curve, in green, the SAGE well with a new stable N+ contact plus the ceramic insert, which gives you even more sensitivity in the low energy region of the gamma ray energy spectrum. While the ceramic insert will be standard, the ultra low background aluminum end caps will still be available for those configurations. So I'll transition to other features and options, but perhaps before I transition, I would like to pause and give an opportunity for people to ask any questions, anything that wasn't clear, or anything that we'd like to have further explanation. Okay, there are no questions at this time, so I'll go on and talk about the additional features and options that are available with the SAGE well detectors. So because of the low capacitance and the low noise characteristics of the SAGE well detector, it's also much more resistant to microphonic effects, which gives us the opportunity to be able to offer the SAGE well detector with any standard cryostats that we have on offer. That including the electrical, the coolers of the CP5 Plus and our Cryocycle 2 offerings. The detectors can be configured in remote detector chambers of a variety of different configurations. We have our standard low background cryostat options, as well as our ultra low background options, and which now include the ceramic well insert. As always, if there's a configuration that doesn't meet your particular needs, we're always happy to work with our customers to develop a custom configuration for your particular application. One of the performance features of the SAGE well is that it works very, very well with our digital signal analyzers. And in fact, it's to get the most performance advantage out of the detector, one requires these digital signal analyzers, such as our Lynx and our DSA. And I want to kind of highlight that feature by drawing your attention to the trapezoidal shaping algorithm that's used within the signal analyzers, and that there's two parameters that are needed to be able to set that shaping time when using these systems. One is the rise time, and the rise time is really related to the noise of the system. So a lower noise system will require shorter rise times than a higher noise system. The second one is the flat top, which is related to the signal collection time. So a detector that has a long signal collection time will have a larger flat top than one with a shorter rise time. To put a context of where the typical settings are for rise time and flat top in coaxial detectors, one will typically see values within about 5.6 rise time, 0.8 flat top, to 8.8 rise time and 1.2 flat top, approximately related to the size of the detector. Usually larger detectors will have a longer rise time, but this is an approximate range of detectors. The Sagewell detector has a unique combination of having a long charge collection time, which requires that it needs a longer flat top. However, it's also a very low capacitance detector, which allows it to be operated at a shorter rise time. So the typical rise times you'll see in a Sagewell detector are about 5.6 microseconds to with a 1.6 microsecond flat top. The part that makes this significant in comparison to the other detectors is that the dead time of a detector system is related, in a digital system, is related to the sum of the rise time and the flat top. And one can see from this is that the sum of the rise time and flat top needed to operate a Sagewell detector is well within the range of a typical coaxial detector. What this means is that if you have a case where you happen to have a higher activity system, you're not going to have any sacrifice in count rate performance when compared to other germanium detectors. So one has a very similar performance with the Sagewell. Another feature that I'd like to highlight with respect to the Sagewell detectors is that it's compatible with our LabSOCS efficiency computation product. LabSOCS has been a very successful product over the years. It's been available for almost 20 years now, and with the advent of the Sagewell detector, we've advanced the LabSOCS product to be compatible with that. It required that we add an additional characterization measurements, such as measuring a sample in the well, so that we can validate that efficiency response. And what this gives you an advantage is that when you have a sample that maybe is a different density or a different material than what your calibration sources have, you can very quickly compute what the proper efficiency response is with LabSOCS and maintain a good accurate analysis. The other advantage of being compatible with LabSOCS is it gives access to Cascade Summing correction algorithms that are available in our Genie 2000 and Apex Gamma software packages. As you may be aware, our Genie 2000 and Apex Gamma have a methodology which allows users to be able to automatically correct for Cascade Summing losses within their measurement. And just to kind of illustrate the dependence of this, as the Sagewell the well detectors have some of the most challenging summing effects, I want to show the example of a relatively straightforward example with the cobalt-60 decay. As you are most likely aware, that cobalt-60 has two characteristic gamma rays of 1173 and 1332. These gamma rays are actually emitted in a cascade event at essentially the same time, and this is unresolvable by the detector. So if you have a case where you detect, for example, the 1332 with its full energy in the detector, if the 1173 happens to enter the detector, even not depositing the full energy, but just part of the energy, then you lose that count out of the peak. And this represents a loss in apparent efficiency, or an actual loss of efficiency in your peak, because these are losses that that no longer show up in the peak area. Now, these are the physical mechanics driving this are well known and predictable if we know the efficiency of the system, both the total efficiency and the full energy peak efficiency, and the radionuclide decay scheme. The decay schemes are known, and so those are included in our Cascade Summing libraries in our algorithms. And the efficiencies are computed, both the full energy peak and the total efficiency, within a special LabSOCS algorithm to estimate that. And one can see here that dependence. This is a efficiency, the efficiency curve again, versus energy for a sample within the well. The solid line represents the full energy peak efficiency. This is the peaks that you see. But the dotted line represents the probability or the efficiency for detecting any amount of energy related to that particular gamma ray. And one can see that this efficiency decreases a lot less quickly than the full energy peak efficiency. And in fact, even at high energies, one can have about, within the well detector, close to 70% of the 70% chance of detecting that gamma ray or having an amount of energy in there. What the impact is in terms of measuring your peak area is represented by this chart, where for a total efficiency on the horizontal axis, we have the total, the correction factor, or the amount missed, if you will, that come out of the peak due to the summing. And if we go up to 70%, we can see as much as a factor of 3 or 4 loss of counts from your peak. So that represents, if you detect if you were expected to detect 100 counts in your peak, you would only see 25 counts or even less. And this, these are real losses in the peak that you cannot easily recover. However, you can predict what they are and correct your efficiency. And to show that, I show the benefit of the cascade summing corrections here. This is an example of a sample measured in the well that contains radium-226 and daughters. The sample was closed and allowed to come to secular equilibrium, so that the individual lines from the radium-226 and the daughters, when analyzed, should give the same activity. And we measured for a 20-minute count time and calibrated with LabSOCS. So the energy lines are shown on the horizontal axis, and the computed line activity for each of those lines is shown on the vertical axis. The open symbols represent the activities that we would compute if we don't correct for the cascade summing losses. And if one were to take those lines and just average them, one gets the average activity of the sample as the dashed line. This would end up, in this particular case, to be 30% below what the actual activity value is. However, by applying the automated cascade summing correction algorithms of Gini 2000 or Apex Gamma, those losses can be predicted and corrected in the computation of the individual line activities and get the results illustrated in the blue circles and get a much more accurate activity calculation. And this process happens automatically within the algorithms and only requires an amount of setup required to define the efficiency or to define the geometry of the measurement. These features are now available with the Sage-Weld detector. Another feature I'd like to discuss is background reduction, and I want to show this slide as a way of introducing into this because everyone I think is quite familiar with the best way with germanium detectors to reduce the background is to put it within a shield, and I illustrate here what advantage that a shield gives by showing the number of counts per second for KeV in a given spectrum versus energy. In an unshielded configuration, you get the spectrum in the top curve, which is, one can see the thallium-208 from the thorium decay series, the potassium-40 from the norm samples. And this is ubiquitous in everybody's gamma ray spectra. Just by putting an amount of shielding, so in steel, one already significantly reduces those effects. One can, in addition, use shield like 10 centimeters of lead, which is equivalent to our 747 and 767 shields, or include even 15 centimeters of lead, equivalent to 6 inches, in our 777 shield. Now, one will notice that the biggest amount of gain in background reduction just comes by putting just an amount of steel, and each time getting increasingly higher shielding, you get improved performance, but it becomes less and less amount each time. That's because the shields are increasingly reducing the amount of terrestrial radiation, which is the passive shielding of lead and steel is quite effective at doing. And but what's remaining is primarily background related to cosmic rays. It's from extraterrestrial origin. Cosmic rays interact in the atmosphere and produce high energy muons that then and neutrons, which then rain down on the Earth. And these are very difficult to stop, even with an amount of lead. And typically, for passive shielding purposes, many people will bury the detector deep in a mine underneath a mountain or very, very deep under the Earth in order to significantly suppress the cosmic radiation. So that's typically not accessible to the majority of us. And so there are ways, though, that we can reduce that through active shielding, through an active cosmic veto. And we have another product called the Cosmic Guard System, which is a system that is quite compatible with the Sage-Weld detector and allows one to further enhance their minimum detectable activities by further reducing the background due to cosmic radiation interaction. And this system takes advantage of the fact that the majority of the cosmic radiation comes from above. So just by putting a panel on the top of the shield, one can already intercept more than half of the incident radiation. We have developed a system that's fully digital and software controlled, so the system is very easy to set up and maintain. We record both the original data as well as the suppressed spectra, so one can very readily check the performance of the system and verify and validate that it's operating properly. And by using this system as an add-on to your standard detector systems, you can reduce your background by as much as 40% over and above what you would have without the cosmic veto system. So I show an example here of a GSW 275 and a 777 shield where we have a measured background reduction of 40% over the standard background. And to put that in context of what that means in the benefit is that, like the background reduction, reducing the background is similar to reducing the time of your measurement. So by reducing a 40% reduction, a 24-hour measurement in the past can be reduced to 16 hours to get the same minimum detectable activity. And that by doing that, that means that one could measure a long sample over the night, and then when one is in the laboratory during the day, one can use that detector system to measure higher activity samples and shorter run samples, and therefore increase the overall utility and throughput of the system. So these are the features that I wanted to present to you, and some of the advantages and benefits of the Sagewell detector. This is just just very bit at an introductory, but I'd also like to point out some additional reading that is available in the public sphere in publications of applied radiation and isotopes, nuclear instruments and methods. It describes some of the features and advantages of these detectors, as well as observations from other customers and users of these systems. And with that, I'd like to have an opportunity for others to ask any additional questions, and before I transfer to my colleague. Is the ceramic, so I have a question, is the ceramic well insert available for existing Sagewell detectors? Yes, this well would be retrofittable on existing detectors. It will have to come back to the factory to have that exchange, but it can be done for essentially an exchange, the cost of the end cap and a vacuum service to restore the detector. Okay, there are no more questions, so I'm going to transition to my colleague, Doug Van Cleef.
Thank you, Will. Thank you, Will. That was nicely done. All right, so I am going to add a few of my remarks to why I think you need one or more of these. I appreciate the opportunity to spend just a couple minutes in front of you talking about this. First, good afternoon and welcome to this webinar. We appreciate all of you joining this. So this application section is really about not selling you a Sagewell detector, but helping you understand why we think this technology might matter to you. Many of you may be aware that I had the privilege of being involved in the startup and equipping of radiochemistry labs in the past, and I'll tell you that I've never bought a well detector. Before you classify me as a hypocrite for not doing that, I actually would like to tell you why, because there is a reason for me not having bought a well detector. So perhaps the subtitle for this talk should be, what's wrong with conventional well detectors? And I'll start with this next slide to answer that question. You already saw this slide from Will. A traditional well detector has very poor resolution compared to what we might consider a laboratory standard detector like a P-type coaxial detector, and much worse resolution than the Beji detector, which is now in use in many laboratories across the country. So if we didn't have such poor resolution in a traditional well detector, we might have considered it for something other than very specialized applications. But because the resolution is so poor, the traditional well detector is kind of a last resort for those cases where we have very small sample volumes or very specialized measurement requirements. If we look at the other slide that Will showed us, with the dramatically improved resolution of the sage well detector, now we can start talking about the sage well as not only a good well detector, but a good general purpose detector or all-around detector. So if you look at that improvement in resolution, right off the bat, the sage well delivers better detection sensitivity because of the impact of the amount of background. As you saw earlier from Will, detection limits increase as the square root of the background counts, or decrease as the square root of the reduction in background counts. And because the resolution affects the number of counts in your background, you could extrapolate that to say that the detection limit improves as the square root of the reduction in resolution, all by itself, nothing else taken into consideration. This is another graph that you saw earlier that kind of highlights the problem with traditional well detectors and shows the dramatic improvement in a sage well detector, which not only transfers to its use as a well detector, but as a general purpose detector. I really believe that if we'd had resolution and efficiency performance like we see in the sage well detector today, most of the laboratories around the country that have maybe one or two well detectors and then a bunch of what we would call conventional germanium detectors would be equipped a lot more with well detectors. So to illustrate the value of the sage well, Will's going to help me out here and show some example geometries as I talk through this. I'm aware that many or maybe most of you know a lot about the basic impacts of improved counting geometries for reduction of counting times or reduction of detection limits. I'm going to run through a few examples here to show you what I think are some fairly significant impacts of those different geometries to make the case for how the sage well detector can help you out. So let's say we want to measure some common radioactive materials in samples, such as radium-226 or 228 in water. I know that's a fairly popular topic these days. There are lots of ways to do this that result in varying degrees of confidence in the results, and that confidence is variable dependent on how much data we get from our analytical method, which is largely dependent on efficiency. So I'm going to use efficiency as the basis for describing some sequential improvements using radium measurements as an example. So let's see if I can be better than the technology here. All right. All right, so here I start by showing a typical absolute efficiency curve for a 1 liter bottle standing vertically on the face of a generic high purity germanium detector. And now we're going to show you a picture of that, I think. There we go. There's a 1 liter bottle on the top of our sage well detector, a classic geometry, one probably everyone in the room who does a gamma ray spectrum analysis has been through before. We're going to look again at that curve. The efficiency curve shows a maximum absolute efficiency down here in about the 150 to 200 keV range of about 0.016 counts or observations for every gamma ray emitted from that sample, or a maximum absolute efficiency of about 1.6%. If we want better detection limits, we can change a counting geometry to something that we know is better. For example, a large Marinelli beaker. Will, if you please. By the way, this is a very large Marinelli beaker. That's a 4 1/4 inch end cap on that sage well detector to accommodate that 28 millimeter well. So this is a 4 liter Marinelli, but the principle is pretty much the same. And what you see is a significant improvement just by adding the Marinelli over a 1 liter bottle. And in fact, it goes to about 0.036 counts per gamma emission, or about 3.6% absolute efficiency, more than a factor of 2 higher than the 1 liter bottle. To make things more interesting, if we could extract the analyte or analytes of interest from that sample and put them on a filter, for example, and then place that filter on the face of the same detector, then we get yet another fairly dramatic improvement in efficiency, as shown in this curve here. Note that we've gone from about 3.6% maximum counting efficiency to about 15%, a factor of 4 improvement over the 2-liter Marinelli and a factor of about a 10 improvement over the 1-liter bottle. We can see from this that the idea that Vern Kahn and his associates had in the 1980s in their development of the Radium-226 method at Georgia Tech had its roots in some good scientific merit here. Now I'm going to, what am I going to do next? Now I'm going to change the topic a little bit from what's wrong with well detectors to what's right with the Sage well detector. And I'm going to begin by taking the graph you just saw, and I'm going to put it on a different scale. So this is the same scale you saw just a moment ago with the 1-liter bottle, the 2-liter Marinelli, and the 52-millimeter filter, except that the vertical axis is now up to 100% maximum efficiency. Why did I do that? So that I could show you this next slide. You can see here, Will, if you please, if we take that sample, maybe we take the filter and roll it up and stick it in the vial, or maybe we just take the precipitate that we were going to put on that filter and put it in that vial and stick it in the well, it dramatically changes, again, our counting efficiency, with the maximum as high as nearly 90% for part of the energy range. And we also see that for the full energy range of this detector, we have substantially improved counting efficiency. I suggest to you that if we had tools like this that worked this well, not only for efficiency but resolution, that the Kahn method would have found a lot more homes than it did over the last approximately 20 years since it's been around. So here's another graphic illustration of what you get by making that transition from, say, a 1-liter sample to putting your sample concentrated in a well. If you look carefully at the vertical axis, it's a logarithmic axis. So we're talking about approximately an order of magnitude improvement to go from a 1-liter bottle to taking that same sample, concentrating it into a precipitate and sticking it in a well. Dramatic improvement in sensitivity here. On the next slide, I want to talk a little bit about some other example applications and the improved analytical performance that can come with them. The first thing I want to do is compare sample vials and wells, bottle samples on end caps and Marinellis, like we've already talked about, with a couple of very specific call-outs on their performance there. The Sage well, as Will already told you, stands for a small anode germanium well detector, and the resolution performance comes primarily from an improved proprietary electrical contact. We get a step change improvement in count time just from the resolution performance and its effect on background. We get dramatically reduced count time with in-well counting, as you saw just a moment ago, but we don't sacrifice the ability to use that detector to do other types of sample analyses like we would have in a conventional well detector, which was only used for specialized samples because of its poor resolution. We have a couple of case studies that we were helped with some of our clients who were early adopters of the Sage well technology. This one here talks a little bit about lead-210 dating. In this example, we're going to calculate the count time to MDA for a Sage well detector, the large well detector that's been used in our examples here, and compared with a traditional well detector. So we're only looking at the improvement in resolution performance to help our MDA. Both detectors have a 28-millimeter diameter well. In the conventional well detector world, that would have been a custom-made detector. Now we have a standard model that has a 28-millimeter well, and I know many of you who are interested in using well detectors are very happy that that's now a standard size. The sample is a sediment in a vial with a 37-millimeter fill height, and you can see in the bottom right-hand corner of this slide the dramatic difference in counting time required to meet a certain MDA, with the traditional well detector being in blue and the Sage well in red. A factor of 4 improvement was realized for lead-210, which is a common analyte used in well detector counting. Next up, I want to do a quick review of the radium concept we just talked about. We take radium precipitated onto a filter paper. That method was approved by the EPA for use in drinking water in 2002, but has been in use in laboratories since the early 1990s. The scenarios that we evaluated here include a 47-millimeter filter from the example method onto a Veggie detector, or taking that same sample and putting the precipitate in a vial and sticking it in a well detector. So we're comparing a good high-performance Veggie detector with a filter to a high-performance well detector with the same sample mass. The detectors have comparable energy resolution, but because of the superior resolution in the well of the SAGE well, we get a curve that looks like this. And you saw the same curve before because I used it as an example. A factor of 8 improvement, nearly an order of magnitude, with a 50x reduction in counting time by using that SAGE well for the same sample. And finally, a quick case study about radioiodine in milk. The interesting part of this case study is that we're not doing anything different with our sample. Now, there are ways to precipitate iodine out of liquid samples. I don't know how well they work for milk. So you might even think about that if you know enough about chemistry to do that well. But in this case, we're just going to take a 30% relative efficiency P-type coaxial detector. There are hundreds, if not thousands, of those in laboratories around the world, and compare it to a 120 cc SAGE well detector, which is going to be about the same active volume. The SAGE well, because of its improvement in resolution over a conventional P-type detector, again, populated in almost every laboratory around the world, results in a factor of 2 improvement in detection limits, or approximately 5 times shorter counting times. And this example could be applied to a variety of different types of large liquid samples, which are best measured in things like Marinelli beakers. And it's a good illustration of the versatility of the SAGE well, not only as truly a next generation well detector, but as a good all-around detector. Okay, I'd like to take just a minute and ask you if you have any questions on that, any of the topics that I've brought up. I think I'm being advised to look in the chat box. Okay. I have a question about reducing the terrestrial background for the detector. Can it be kept underground? And would that, I think that question is, can it increase the consequences of radon progeny? The answer is yes, it could if the radon were allowed to collect and accumulate in that facility. Almost every facility, whether it be above ground or below ground, that has to deal with radon progeny is going to be forced to find a way to evacuate the radon progeny from the vicinity of the detector by some means. I hope that answers your question. Any others? Well, I think I'm getting the message to scroll down and look, but I don't see any other questions. Price? Is that the question? Sorry about that. Price difference for ceramic and aluminum well. I'm going to have to call on my colleague Will to answer that question. I think they're going to, as of today, those prices are the same. So if you order, if you're ordering the ultra low background option for a SAGE well detector and you want a ceramic insert instead of aluminum, all you have to do is ask for it. Correct answer? Very good. I like it when I get a correct answer. All right. Anybody else? My call screeners over here are working on another question, I think. It hasn't made it to me yet, so we'll take a look. Just a minute, please. Does it require liquid nitrogen cooling? Is that the correct question? Well, yes, of course, all germanium detectors require cryogenic cooling. This is the first line of commercially available well detectors that can also use electromechanical cooling for them because of the features that Will talked about earlier. So it does require cryogenic cooling. It does not have to be from liquid nitrogen. It is compatible with our cryopulse and cryocycle systems. I hope that answers your question. No more questions? Okay, very good. I thank you very much for your attendance. And I do want to advise you that all of these webinars that we do can be found for your review again in the future or to share with colleagues at canberra.com/webinars. Thank you again for your attendance. we appreciate having you in this seminar. Have a great day.